So page 7. We went through conjugate method. Let me just highlight the steps, and then we'll practice more with this on the next page. I just want to kind of briefly review, and then there's one more type of whole, or one more type of method that involves complex fraction that we can go over next. So we know that when there's radicals involved, we really can't, there's not any factoring that we can do. But after direct substitution, if we realize that there's a whole, we know that we've got to find a way to cancel the whole between numerator and denominator. In this problem, denominator is very useful and helpful. We know that you can't do anything with x minus 4, and you can obviously tell that x minus 4 is causing the whole, which means that there must be an x minus 4 hiding in the numerator that's also doing the same thing. And we identify the conjugate, which is simply the numerator expression, but just changing the sign between the two terms. So we identify the conjugate, multiply by the conjugate, but whatever you do to the numerator, you got to do to the same thing to the denominator to maintain balance. And then we're going to expand. So when you expand, first pairs will get multiplied together, and then your last pairs will get multiplied together. Don't worry about the middle pairs, because those will just cancel out. The subtle thing that we have to watch out for in this problem is make sure that anything following a minus sign, you got to protect your expression with a set of parentheses. Otherwise, you may forget to distribute the negative through. So once the negative distributes through, combine like terms, then you're off to trying to identify a way to cancel out the expression that's causing the whole. And if something is still a little bit off, you may have to factor either a number or something out in order to get that perfect match to show up. And once you get that match, then you reevaluate, and then that should get you down to a real number, where before it was giving you initially a 0 or 0. And notation wise, we want to use arrows to indicate, and we always want to do direct substitution. And then your limit notation would need to be rewritten every time there is an x in the expression. So technically, I should have had a limit notation here as well. And then you can stop writing your limit notation as soon as your expression is down just to a number. Once it's down to a number, once the x's are gone, you can drop the limit notation. All right, example 2. This is simplifying by using common denominator. So let's just jump into it, and we can kind of figure things out as I will show you the steps as we work through. I'll do this on a separate sheet here. All right, first steps first. What's our first step? Plug in the 0, right? We don't know what's going on. Let's go ahead and figure out what's happening at 0. So 0 in for x, I get 1/4 minus 1/4, which is 0. And denominator is also 0, which means that there is a what? There's a whole, right? Which means there's a whole. It's preventing us from seeing what the limit is, but there is a limit. We just haven't found it yet. The hint is this denominator. This denominator is showing an x. You can't do anything with an x. It's already reduced. The x is obviously causing a 0, which means that there is also an x hiding in the numerator that's causing a 0. But we have to do a little bit of cleanup to have that numerator show us where that x is. So what we're going to do is we're going to kind of step to the side and just focus on trying to clean this piece up. And what I mean by cleaning up is we're going to trying to merge the two fractions together. And if I want to add and subtract fraction, I need a common denominator. So I'm going to just step to the side here and focus on just that piece of our problem. So if I want to find a common denominator, I need to find something large enough that both individual denominators can multiply into or can be a factor of. So what could be a common denominator, or what is the common denominator for these two individual fractions? More than that. Yeah, I need 4 and I need the x plus 4. Now, if it was 4x, then yes, then you just take this denominator and make it the common denominator. But anytime there's a plus, we really need to treat this as independent of the 4. We need to treat the x plus 4 as separate as 4. I know we see the 4s in both of them, but that plus 4 is not the same thing as just that 4 by itself. So these are completely different denominators, which means that we need both pieces to create our common denominator. Okay, so now comes the balancing part. We need to figure out what do we need to do with the numerator to balance the fractions so that we're still ending up with the same overall individual fractions as what we started with. Now, this denominator x plus 4, how is it different from this new denominator? This one is missing a what? A 4. So I need to balance the numerator out by multiplying the numerator by 4 as well. So 1 times 4 is 4. So now I have my fraction balanced. This is the same thing as 1 over x plus 4, because if I cancel the 4s out, I'm back to where I started. So I haven't changed my overall value. What's different between this denominator and this denominator? X plus 4. So I need to balance the numerator by an x plus 4. 1 times x plus 4 is just x plus 4. We do need to protect it with the set of parentheses. Otherwise, we may forget to distribute that negative through. Okay, so now our goal is to merge these two into the same fraction. Now we can, because we are sharing the same common denominator. Now we can just combine and our like terms from the numerator. So this is what, 4 minus x minus 4, because I'm distributing the negative through. And what is my numerator going to just turn into? Negative x over 4 times x plus 4. So we're not done yet, but we are making progress. We're going to take this cleaned up numerator and put it back into our problem. So these are the same things, but this is a lot more useful for us because we merged it into the same fraction, where before this disconnected parts makes it difficult for us to see the behavior that we want to see. So now I'm going to go back to the problem here, rewrite the problem. I'll replace this piece with this piece here. Divided by x. Okay, good so far? Now we know that x is causing the whole, and then if you look, we are beginning to see that x show up, right? Before it wasn't showing up, and now it's a lot more clear as to what could be the target for us in terms of canceling out. But it's still sitting in a complex fraction. It feels a little hard to see exactly the relationship between these. So why don't we try to bring this up to the same level? So dividing by a value is the same thing as what? Multiply by the reciprocal. So if I multiply by the reciprocal, then I can bring this x up to the same level as this fraction, and then it's easier to see the relationship. So so again, dividing by x is the same thing as multiplying by 1 over x. These are the same things. It's a lot easier to see the relationship between the variables, where this feels a little bit more complicated. But now that we're at this stage here, again, I'm rewriting my limit statements each time that I am cleaning up or each time that my variable x is showing up. Now what can we do? You see anything that cancels out? X, yeah. But there's still a what left over in the numerator. Still -1, right? So the x's goes away, but there's still a -1 there. But this is good because we've removed the whole. And if we remove the whole, we should be able to avoid getting 0/0. Now we can reevaluate. Let me just rewrite this again, just for us to see exactly our reduced expression. You don't have to, but just for cleanup purposes here. Now that we have our reduced expression, we should be able to get something other than 0/0. What's our final step? Direct substitution, right? So 0 in for x. My denominator ends up giving us what? Oh, yes, question. Go ahead. What's my cleaned up answer? -1/16. As soon as my variables disappear, I can just write the number down and I can drop the limit notation. I think this is the most difficult in the sense that there are a lot of steps involved, and you got to deal with fractions, you got to deal with common denominators, and it's the longest process of the three that we've seen. Right, the factoring, we started off with that was the easiest. Conjugate was manageable, and then this is the most time-consuming one. So again, we always start off with direct substitution, convince ourselves that there's a whole before we do anything else. If we see a complex fraction, we know our first step is to try to get that numerator fraction to clean up itself in terms of common denominator and merging into the same fraction. Once it's down to one fraction, we can think about trying to match the numerator and denominator, multiply it by the denominator's reciprocal, and then we should be able to get a common factor to pair up and cancel out. Once the whole has been removed, reevaluate, and we should be able to get down to a real number. All right, any questions? All right. There's another theorem that I want to go over. This is called the squeeze theorem. I think this is pretty easy. It's always going to follow the same steps. And let me just kind of go through what this is saying. So in the graph below, you have a lower and upper function with the same limit value at x equals a. So first off, there's three functions that will always be defined relationally. There's always going to be an upper function, a middle function, and a lower function. So there's always going to be this relationship that the problem is going to give you at the very beginning. It's always going to be a function that's always less than or equal to a middle function, which is always less than or equal to an upper function. And the three functions will always stay in their place. So the idea is that what if we don't know, what if we're trying to find the limit of the middle function, but we don't have details about the middle function, but we do have details about the upper and upper and lower function, we can actually find the limit. And it's called the squeeze theorem because if the upper and the middle limit are the same value, then the middle one has to also share that same value. So the idea is that if my upper and lower functions share the same limit, the middle function will, in a sense, get squeezed between the two. And if it gets squeezed between the same two numbers, it also must share the same number. So here's an example. Let h of x equals 1, f of x equals x squared plus 1, but we're trying to find the limit of the middle function. We're trying to find the limit as x approaches 0 of g of x. Okay. We don't know what g of x is, but we do have details about f and h. So we'll just go ahead and find the limit of both these functions. So this is the way I want you to set it up. You'll do it the same way every time. We're going to put a limit in front of each of these functions and then write out the relationship that we see. So we'll do the limit as x approaches 0 of f of x, which is less than or equal to the limit as x approaches 0 of g of x, less than or equal to the limit as x approaches 0 of h of x. All I'm doing is I'm rewriting my same relationship. I'm just putting a limit in front of each of my functions. Now I'm going to put the details for f and h in based off of what they give me. F is just x squared plus 1. My middle function is still unknown. And then my upper function is just a 1. The middle is still unknown, but we can make some progress with the lower and upper. Direct substitution, what is this going to give us? Just 1. So I can say 1 is less than or equal to the limit as x approaches 0 of g of x is less than or equal to. Here, there's no variable to plug in, so this will always still remain as what? What's my limit here? 1, yep. So my value is always staying 1. There's no variable to plug in for h. So if my lower limit is 1 and my upper limit is 1, my middle function must also be what? 1. So we can say by squeeze theorem, the limit as x approaches 0 of g of x equals to 1. Even though we don't know what the g of x function is, we are able to arrive at this conclusion because of the relationship that is established, and also because the upper and lower share the same limit. So there's only two results that can occur with these types of problems. Either these are the same value and you can identify what the limit is, or if these are not the same value, then we'll just say the limit is inconclusive because we don't have enough detail to know exactly what that number is if you're giving me a range of two different numbers. And then with squeeze theorem, it's always going to be this relationship, and you're always looking for the middle unknown function. There's never a situation where, oh, I got to do something, find the unknown lower or the unknown middle. It's always the unknown middle. Sorry, it's never the unknown lower and unknown upper. It's always the unknown middle. And you're just finding the limit of the outer functions, and you can either make a conclusive limit value or you can't, depending on what the upper and lower gives you. And that's it. Nothing crazy. All right. Okay, so we're just going to practice today with our three main categories of functions that, for functions that have holes, we have these three categories. It could be GCF factoring, it could be conjugate method, or it could be complex fraction, common denominator. But we never want to skip our first step, right? We never want to skip direct substitution because something may be disguised as a conjugate or a complex fraction problem, but it may end up just giving you a real number. If it gives you a real number, there's no need to go through all those steps. And if you jump into the steps of conjugate and factoring and complex fraction and reducing, you're making a big assumption. You're making an assumption that there's already a hole. And then if you make an assumption that there's a hole and there ends up not being a hole, that's going to throw you off and it's going to be hard to get back on track. So make sure you always do direct substitution first. Convince yourself that there is a hole before you go into all the other steps that's involved with cleaning up and identifying and removing that hole. Okay, so go ahead and try number one. I'll work through number one the same time that you do. And then we'll do 1 and 2 where you're working on your own and then you're looking at my work. And then we can shift into me just kind of circling the room and seeing how we do with our steps. And I've highlighted the steps up above, so you can look at that as well as you follow, as you decide what you want to do next. Okay, and also pay attention to your notation. Know when to rewrite your limit statement and know when your limit statement can drop off. Sorry. Check your steps, check your work. We have to convince ourselves that there is a hole before we go through all of our algebraic steps. We do have confirmation that there's a hole at x equals 4 with that 0 over 0, multiplied by the numerator and denominator by the conjugate of the numerator. Expand out your numerator, but leave your denominator alone because you already know the x minus 4 is ready for the reducing and canceling out process. If we FOIL out the denominator, we lose that factor that is ready. When you eliminate between numerator and denominator, you can reevaluate your expression. Then no need to rewrite your limit statements once you're down to numeric values. If you feel like you need more space than what I'm giving you, feel free to do your work on a separate sheet. All right, any questions with 1 or 2? All right, keep working. I'll just see how you guys do. Yeah.
The last number. But what's canceled?
I'll put on the board. Okay. Read that out to me.
It's 6 minus the square root of x plus 32. And then you have the reciprocal.
I'll
Or the
conjugate.
conjugate.
I said first pair and last pair. Let's just do everything out. So this one, this one. So we know there's 4 pieces to it, right?
Mhm.
Okay. First pair. Plus. These two. And then these two.
Yep. Yeah, that makes more sense. I see it.
So we know this is always going to go out, which means that you only have to worry about this pair, and everything else is.
Thank you.
So I need to card system plus 2. So make sure you conjugate the column the exact same. We just change this sign. So your conjugate is. Pull it up. Excellent. You guys are all taking the first step, direct substitution. That's good. We're going to get problems that are even more complicated than this, and it's always good to establish that first step, no matter how much distraction is around you. So. All right, any questions with 3 or 4? Okay, for practice purposes, all these problems are ending up having holes, just so we can get that practice, but we can't assume that, okay, that's gonna be always be the case. So on the quiz, you may see some limits just giving you a real number, which means you stop, or it may give you like a 10/0, which you would say the limit doesn't exist. And then those would be intermixed with problems that is 0/0. So it's important that we always take that initial step, because even though this sheet is showing all 0/0, on the quiz, it may not be that way. So direct substitution is an important first step that can help you quickly categorize what you're working with. All right, any questions? So tomorrow, we're going to go through a full quiz review. So you kind of have a class period to practice all the different things that you may need to do, which is these types of problems, and then being able to look at a graph, identify a limit, and also being able to sketch a graph based off of property. So that's what your quiz will look like. We'll work on that tomorrow. We'll do the quiz review worksheet that's in your packet. There's homework tonight. So if you look on your calendar here, same exercise pages, but you're just doing 53 to 89, just those 4 problems. And then your AP practice for 1.2 follows immediately after your exercise pages. Now, you may see these types of problems. We haven't gone over what that plus and minus means in the exponent. They basically just mean one side of the limit, but just ignore it and then just treat it like you don't see those exponent notations. So just go through direct substitution. If there's issues with understanding, some problems may not resolve itself with that, but just go through that step and especially on the AP practice, there may be some problems like that. Okay. All right, come get your phones. Again, the solution key is on the website where I have these solutions where you can check your answer. Okay.